It consists into sucking the vesicle with a high enough diameter, about 20 to 30 micrometers, into a smaller micropipette with diameter 2 to 6 micrometers, and the projected on the micropipette length. The dependence of this projected length on the pressure difference in the exterior of the membrane and interior of the micropipette gives us an opportunity to calculate the bending elastic modulus at low sucking pressures and the stretching elastic modulus at high sucking pressure. So using this technique, we have one of the biggest achievements of the laboratory is that we measured for the first time the stretching elastic modulus of a monolayer on the interface with motion droplets of the kind oil in water. So this is up to our knowledge, not repeated till now. And because of the insolubility of oil in water, the volume of the emulsion droplet is kept constant during the experiment. And this is the only way to measure the stretching elasticity at pure water. So we measured this at pure water and also at 180 millimoles sucrose concentration, which is typical concentration for this method. And for the first time we showed that the sugars influence the elasticity of the membranes. So one of the limitations of this method when used giant vesicles is that the volume during the experiment must kept constant of the vesicle. That's why for a long period of time a lot of researchers used a big quantity, for example this one, of sugars to keep the volume constant during the experiment. So now we know that this must be taken into account in such experiments. The other technique, which is for measurement of the bending elastic modulus of lipid membranes, is the thermally induced shape fluctuation method. So the mean squared amplitudes of the fluctuations are inversely proportional to the bending elastic modulus of the lipid membrane. Using this, we have two main achievements of our laboratory using this technique. One is that we improved the technique by adding a stroboscopic illumination, which permits to register a momentum picture shape. Okay, using this we can, it permits to measure the instant picture of the shape of the fluctuating vesicle. And also we have a homemade software for data acquisition and data processing. Also using this technique we measured the influence of different concentrations of different sugars on the elastic properties of lipid membranes. And now we know that all the sugars influence the elasticity of lipid membranes, and the influence is sufficient, so it must be taken into account. So for the last 5 years in our laboratory we have more than 30 publications. Thank you for your attention. You can ask
So here
questions.
we presented also 3 publications cited more than 400 times, but they are out of
We have a
this
theory also.
period. So just for information.
Pay attention to the fact that the mechanical properties of these extremely thin objects, they are nanometers thick, 5 nanometers, they are unmeasurable in any other way. You are bending elasticity, for instance. You are unable to measure such a small value of bending elasticity any other way, but just looking at the shape fluctuations of the vesicle, which are produced by Brownian motion. So just looking at the Brownian motion, you are able to extract such.
What you do is to make statistics out of that.
Yeah.
Yes, they have. So you see there are several peaks, which means that the vesicle is unilamellar or bilamellar or trilamellar.
How do you know that? By hand? I mean, one by one? Or
No, they have a dedicated software about
that's
it.
software about it.
Yes, they choose the contour, the computer is finding the contour, and then there is
measure the area.
analysis of the
Area.
positions of the contour, of how many images you use typically.
10,000.
It depends on the kind of experiment. It could be between 400 up to 10,000 different images. 10,000 and we to look for the time variations of different images. The apparatus, the needs to measure it, and the other possibility to measure it using stroboscope. Because in the case for the elasticity only, we have derived Kenzler's formula which connects the amplitude observed when the exposure time is long to what amplitudes we will observe it if it is an instant image. This formula is working for the means, not for the dynamics. So for the dynamics, we need this is